Good day, everyone. We are reviewing Wetzel's Limnology textbook, edition number 4. We are on chapter 8, which deals with water movements, and more specifically today we'll be looking at subchapter 4, modeling water movements. Water movements are modeled to improve understanding of discrete physical processes such as the internal bores in figure 8-27, or the temporal variation of the full range of physical processes occurring within a lake or a river system. To meet these goals, models have different degrees of complexity. In some cases, all the terms that affect water flow, both advective and turbulent, are included as when modeling discrete processes. For full lake and river models, simplifying assumptions are essential to reduce computational costs. Modeling is based on using conservation equations for momentum and continuity. For example, upward motions are balanced by downward ones. A critical simplifying assumption for full lake models is that hydrostatic pressure, that is the pressure on the lake from the weight of water and overlying atmosphere, exceeds the changes in pressure from motion such as acceleration, the non-hydrostatic pressure component. Neglect of this term in model of lakes and rivers mean that they can be modeled as parcels of water and gridded with a much larger horizontal depth scale than in the vertical, albeit with care required in selecting these scales. As with all models, outcomes require validation with observational data or theory. Equations in the model include changes in velocity with respect to time, advective and diffusive transport, changes in density, force per unit mass, and shear stress on the water surface and within the water column. The terms included depend upon model complexity. For studies of full lakes and river system, 1D or 3D hydrodynamic models are usually applied. Hydrodynamic models. Hydrodynamic models are used to describe the physical processes within lakes and rivers and their changes over time. They are used to better understand physical-biological coupling in lakes and are increasingly being used to predict changes in thermal structure and mixing under climate change, and for decades have been an essential component in predicting changes in water quality required for water management. Hydrodynamic models applied to lakes and reservoirs can be one-dimensional, 1D, 2D, or 3D. Examples of 1D model include DYRESM, so all those are like examples of models. Model of reduced dimension, 1D, 2D, use vertical depth or horizontal averages to reduce computational time. For 1D lake models, the assumption is that horizontal density gradients are small relative to vertical ones. Lake numbers can be used to check the validity of the 1D assumption under strong winds, when the upwelling of the lower layer indicates that modeling with higher dimensionality is advisable, including accounting for boundary mixing at the thermocline. In contrast, in 1D models of rivers, an assumption is that vertical density gradients are smaller than those in the horizontal. Processes such as up and downwelling of the thermocline or internal wave breaking are not explicitly identified in 1D models due to horizontal averaging. To compensate, approaches to capture the resultant shear and mixing are included in some 1D model. Let's see. Meteorological data required for the models includes shortwave and long-wave radiation, air temperature, relative humidity, and wind speed and direction. Temperature profiles are needed to begin model simulation, and time series data are needed for validation of model output. Meteorological data are sometimes collected from locations distant from the lake of interest, and these data may need to be adjusted to improve model comparison with in-situ data. This approach is often relatively successful if there is a network of meteorological stations in a region. The use of a non-lake meteorological station with 5 minutes average data, and in some cases the use of high-frequency sensors with digital data loggers, enables direct calculation of fluxes, of momentum, and of sensible and latent heat exchange, which can be used to validate the calculations for these variables based on the algorithms in the model. Small lakes and rivers can be sheltered by riparian vegetation or hills, which reduce radiative fluxes, surface water temperature, and winds requiring modification of the radiation input and correction of wind in hydrodynamic models. Heat, momentum, and mass transfer coefficients provide the link between meteorological input data and heat content and movement of water simulated by hydrodynamic models. Early reports form the basis of many of the transfer coefficients used in current hydrodynamic models. Considerable research since that time has quantified how the coefficients vary with atmospheric stability. Varying accuracy in quantifying surface heat fluxes led to appreciable discrepancies in thermal structure and mixing when 1D models were contrasted with measured data on Lake Kivu. Such comparison and subsequent tuning led to model improvements. Recent texts provide valuable insight into how to interpret and quantify meteorological data. Attributes of inflows and outflows are additional inputs to rivers and lake models. For rivers and lakes or reservoirs with large hydrologic flows, accurate specification of the volume of discharge and density of the inflows is critical, as the conditions within the model domain depend on those at the boundary. For all lakes, the density of the inflow and discharge is important for resolving the depth of insertion of the inflow, overflow, interflow, or underflow, and the entrainment of the inflow with the adjacent lake water. Model input data related to outflows usually requires information on the volume of the discharge, which will be known for reservoirs and some lakes, and the depth of the outflow relative to the surface of the lake. Many times, the discharge at the outlet is a model result and can be compared with available discharge data for validation. In reservoirs, the density of the outgoing water from deep outlets depends on the density stratification in the lower water column and the speed of withdrawal. Recent model improvements have included modules for the prediction of snow and ice cover and sediment heating, with additional appropriate inputs such as temperature sensors in the ice and sediment. Evaluation of 1, 2, and 3D hydrodynamic models includes comparisons of the temperature and thermal stratification over periods of time ranging from days to several years. For example, the evaluation of SimStrat, a 1D model that explicitly parameterizes the wind energy transferred to internal waves and the resultant mixing in the benthic boundary layer, was conducted in 2 steps. Results from the upper 60 meters of the 5.2 kilometer square Lake Baldag illustrated that the model correctly simulated temperatures, the depth of the upper mix layer, and seasonal thermocline in the stratified period. The onset of fall cooling and the onset of the stratified period, simulation in 34 meter deep Lake Apnach extended to the bottom. While the modeling could not resolve the internal wave motions, it correctly simulated temperatures and thermal structure throughout the lake, calculated eddy diffusivity using the heat budget method, and simulation were both 3.5 by 10 to the minus 5 meters square per second in the benthic boundary layer, an order of magnitude higher than in the interior layer, attesting to the accuracy in incorporating enhanced internal wave-induced shear and mixing in this region. Yist and Imberger extended the 1D dynamic reservoir simulation model to simulate internal wave-induced mixing and resultant increased fluxes in the benthic boundary layer by parameterizations using the lake number, whose interpretation is similar to that of the Wedderburn number. Their effort was successful in modeling the thermal structure in Mono Lake and Lake Kinneret, both of which have surface areas of approximately 150 kilometers squared and frequent events with lake numbers approaching 1 during the stratified period. Considerable additional development has occurred in these models and others, including incorporating other hydrodynamic processes as described in this chapter. Comparative studies have quantified the accuracy of the same 1D model in lakes at other latitudes, and a suite of models for one lake. Research studies indicating which models need improvement in calculating heat fluxes and any tuning parameters. 3D hydrodynamic models are validated against observational data with a thermistor chains deployed at multiple sites in a lake. Example of such careful, let's see here. validation for the estuary lake and coastal model outcome includes studies by Hodge and all these authors. The rotation of the model Kelvin wave in Hodge is quite similar to that of Mortimer. Okay. So this is figure 838, measured and B simulated temperature and thermal structure in Lake Baldec in 1995. So this is the measured graph, and then this is the simulated one using a model. So this is computer-based, and this is actually observational data that was taken. And you can see that it's pretty similar, at least in general term, right? So we have kind of the same event that has been modeled. It's not exactly the same. It looks like, for example, the heating event was mapped a little deeper in the model than it is in the observational data. And of course, we don't have that resolution here. Like we have very fine resolution in terms of temperature. We have a very smooth line here. But we still also have like a period of non-stratification here that is acknowledged. Actually pretty long, but from November 1995 up to like late April 1996. So that kind of gives us a pretty good amount of trust in those models. And then this figure is the time series of the coefficients of eddy diffusivity in Lake Baikal, Russia, simulated with the one-dimensional model SimStrat. So numbers indicate features of the stratification. One, formation of a thermocline. So we have a formation of a thermocline here with weak mixing under the ice. So we have an ice cover. So this is depth, this is day of the year. So this is pretty close probably to a full year, from 0 to 350. With weak mixing under the, okay, and then this is the vertical diffusivity. So this is not temperature, right? So this is the Kz factor. With mixing, okay, so formation with weak mixing under the ice. So here we don't have a lot of mixing going on. So our Kz is very low. Then in 2, we have formation of a thermocline in the summer. So 2, we have formation of a thermocline in the summer here. So right here is a thermocline. And 3, we have increased mixing and depth of mixing under the ice due to penetrative convection in the spring. So we have increased mixing due to, as they say, penetrative convection, so in the spring, so where the sun is penetrating to the ice and starting convection in the spring. So we have then, therefore, some amount of turbulence going on here in the deeper part of the lake. 4 and 5, deep mixing from convection after ice off. So 4 and 5, we have deep mixing here going on. After the ice is removed, there is no ice, as you can see. And 6, increased mixing deep beneath ice under low density gradients. So this is kind of like where we have mixing like really deep in the lake. I mean, we're dealing like with depth between 200 and about 310, 320 meters. So that's at least like 900 feet, something to that fashion. And so we are still under the ice, and we have some mixing going on. And as we saw before, we also have in the winter it's reverse, right? So we have warmer water at depth than we have at the surface when there's an ice layer. Okay, let's see. Choosing 1D versus 3D models. Hydrodynamic models are used to predict thermal structure and water quality over various timescales and to further ecosystem understanding. They can be used to predict the future states of lakes under the influence of climate and land use change. These predictions can be valuable for water management and weather prediction. The degree of stratification and ventilation of the lower water column can be simulated to identify whether anoxia will become persistent in the hypolimnion or the fate of greenhouse gases. There are trade-offs in selecting 1, 2, or 3D models. Selection depends considerably on the goals of the project. Computational time is one consideration. For instance, the computational time involved in running 3D hydrodynamic models is high. Hence, 1D models are often used to predict the consequences of climate change. An alternate approach is to run 3D models at less frequent intervals over, say, 5-year intervals over a 100-year period. Given the simplifying assumption made in 1D model, comparison with respect to future predictions are often made with several models developed with somewhat different conceptual underpinnings. Thus, if predictions are similar from the diverse models, there is more confidence in the results. 1D models can provide time series of the coefficient of vertical diffusivity, which enables a better understanding of the biogeochemical and biological processes. For example, the estimate of Kz made using SimStrat for Lake Baikal show relatively low values of Kz under the ice in early winter and increases to values of 10 to the minus 2 meters squared per second due to penetrative convection. After ice-off, high values of Kz are found to depth of nearly 200 meters. Once summer stratification sets up, they are only high in the surface mix layer. These changes are mirrored in measurements of chlorophyll A and Secchi depth obtained as time series data in other years. Both indicates increases in biomass when light increases in spring and diatoms in offshore waters are maintained in suspension by the turbulence from penetrative convection below the ice. They also indicate decreases in biomass with deep mixing that transports cells to depth with insufficient light for growth. Biomass increased again in summer with a decreased depth of mixing, although species composition would differ. 3D models also lead to improved understanding and visualization of hydrodynamic processes. It can be an invaluable tool in ecosystem studies. The following example from Lake Janoaca, a lake within the Amazon floodplain, illustrate the importance of wind-driven motions in the 40 kilometer square main basin and of differential heating and cooling within an embayment. The example from 24-meter deep Lake Pleasant in New York illustrates the importance of upwelling from internal wave motions for the movement of dissolved gases to the air-water interface. Wind-induced currents transported water warmed by solar radiation across Lake Janoaca, such that the upper mix layer downwelled to a depth of 2 meters in the 4 to 6 meter deep lake and led to a temperature difference across the lake of 2 degrees centigrade in the afternoon. On relaxation of the winds, or with a change in wind direction, the thermocline downwells in another direction. The sustained up and downwelling means that there are cross-basin flows, as in figures 820 and 821. The upwelling of water from deeper depth enables exchange across the air-water interface. That is, if dissolved oxygen has become undersaturated in the lower water column, it can be replenished by the flux of oxygen from the atmosphere during upwelling. Similarly, fluxes of dissolved gas such as CO2 or CH4 methane can evade during upwelling. Thus, 3D model provides perspective important for ecosystem level questions, and in this case with near surface shear and dissipation rates as additional outputs of the model's more accurate prediction of the fluxes of climate forcing trace gases can be made than are possible for one station alone. So let's see here, we have 840 figure, plan view of a simulated surface temperature and wind velocity. So we have surface temperature here and wind velocity. So let's see, so probably 1 and 2 are the transect, I would think. And so let's see, and wind velocity inset. Okay, I see. So this is the inset. So the surface temperature is here. This is the lake at like somewhat of an oblique angle, if I may think, I guess, or maybe just a an aerial view of it, although it looked like there's an angle to it. But anyway, so the y-axis is the latitude, and the x-axis is the longitude. And so this lake is located close to the equator, although it's south of the equator because it's negative latitude. And the longitude is in the 60s, in the negative 60s. So that is in Brazil, okay? In the Amazon basin. So here we have, warmer part of the lake, the cooler part of the lake. The difference in temperature is about 1 to 2 degrees centigrade, so not that much. And this is the wind speed in meters per second. And so the wind direction, I believe, is coming in from the southeast, going to the northwest. B, simulated temperature at 2 meters. Okay, so this is B, simulated temperature at 2 meters. So this is 2 meter depth. That's the surface. This is 2 meter depth. So we still have like a hot spot here, but then we have cooler waters, and cooler is relative here. It's only like 30 degrees. I mean, it's only like 2 degrees below the coolest at the surface. And so then this is the distribution of it. C, incoming shortwave with snapshot at time of blue vertical dashed line. Okay, so this is the shortwave radiation. So then now we are dealing with watts per meter square, and we are dealing with time on the x-axis. And so therefore we're looking at the sun. So the sun rose on that day at about 6:30 and set at about 6 p.m. So that makes sense. It's close to the equator, so you should have a day that is very close to 12 hours a day and 12 hours a night. And then we probably have some cloud cover, so therefore you have like dips in the solar radiation, and then this is probably solar noon right there. Yeah, noon exactly. And so let's see here. Incoming shortwave with snapshot of blue vertical line. So the blue vertical line snapshot, okay. D is the wind speed, WS black line, and wind direction. So wind speed in black and wind direction. So you can see that the wind direction varies. It goes north and west and doesn't have a lot of east direction as far as I can tell here, a little bit of southern. And then in red, and wind speed in red, and wind direction in red. Okay, got it. So the wind speed increases. So there's also a response of the wind speed to the presence of the sun. So for example, at solar noon, we have like we have pretty high wind speed. And then the last one is ENF. Let's see, ENF, cross section of temperature. So these are the cross section of the temperature in the vertical lake on axis indicated by dashed lines. Okay, so one is this one, very likely, the cross section on this one. So we have from the dashed line, so let's see here, the cross section, so dashed line on axis by dashed line, label 1 and 2. Simulation R4, okay. So this is 1, so this is probably for 1, and I'm assuming that this is this end of 1, and then this is the other end. So you can see, the warm water, the penetration of the warm water here is about, like about 7 meters, and then it shallows out, have cooler water. And then this is number 2, which is cross section north-south, and the same kind of output. Okay. Adding numerical tracers to 3D models can provide additional perspective on the physical processes which moderate ecosystem function. Tracers are quantitative tools that illustrate the flow path of solids or particulates. For example, dissolved gases can be produced by respiration associated with the roots of floating vegetation along the shores of Amazonian floodplain lakes. The water under such meadows is cooler than offshore water and can sink to a depth of neutral buoyancy and then flow offshore. During the day, water in the beds warms more than the adjacent offshore water and flows offshore. At night, the dissolved gases can be mixed vertically in the open water and evade to the atmosphere. Thus, the combination of differential cooling and differential heating leads to the offshore flow of dissolved gases, and mixing by penetrative convection brings them to the air-water interface where they can evade. The addition of a tracer for CO2 when modeling thermally stratified Lake Pleasant showed the upwelling of cold CO2-enriched water in the upper mix layer of the southern basin when winds were from the southwest, and the cross-basin differences in temperature and CO2. The presence of an island precluded the northerly flow of appreciable quantities of the dissolved gas. Accurate estimates of CO2 emission need to account for spatial variability in concentrations. Applying 3D models can improve ecosystem understanding, and in cases such as these, the modeling will lead to improved estimates of emissions of climate-forcing trace gases. And that will be it for today, and we'll talk to you tomorrow, and we'll go over the applications of 1D and 3D models, section D of chapter 8. Thank you, and have a good day. Bye.